Alright, let's take a look at Leetcode 153 and 154. I'm not going to actually look at the problem description for 153 or anything because it's pretty much the exact same thing as 154, and you have to know how to do the first part of this problem, 153, in order to do 154. So I'll pretty much quickly go over how to do that in this problem solution as well. So yeah, after you watch this video, you should be able to complete both of them without any trouble. The only difference between the two is that in this second part, the input list can contain duplicates, and we'll see how that affects our code. It's only going to affect like 1 or 2 lines, but I'll explain that later. So we're given an input array, a sorted list, and it's been rotated at some pivot point. So, you know, as you can see, maybe a regular sorted list would look like this: 0, 1, 2, 4, 5, 6, 7. But we're given something like this: 4, 5, 6, 7, 0, 1, 2. So it's still sorted, but it's been pivoted at one point. So at one point there will be a number larger than the next number, and then it'll continue to be the regular sorted fashion. Yep. So we need to find that minimum element, so basically where it pivots. Alright, so you know, this problem, I mean, it doesn't tell you the constraints, but you can assume that it's going to be a binary search variation, because you know, with any sort of sorted list, you know, you can do better than O of n time. So you know, if we were to brute force it, we could just literally just go through and just look at each number and then see which one is the lowest, but that defeats the whole purpose of the problem. So let's see how we can use a binary search variation to solve this. So first I'm going to kind of just go through a quick I guess review of a binary search algorithm. So on this side here I have 4 different examples. So I have a regular default binary search example, then I have a example from part 1 of this question, then I have an example from part 2, and then another example helping reinforce your understanding for part 1 to whatever, for both. So let's look at how we do the regular binary search. So you have a left pointer at the beginning, right pointer at the last index, and then the midpoint is just the, you know, left plus right divided by 2. And you know, with any sort of binary search problem, it's kind of you shouldn't necessarily memorize the binary search implementation. You should kind of just walk through it like this, and you know, because you know, when you handle a lot of pointers, then you know, things can get messy in your head if you try to memorize. So always kind of just draw out a picture or something and then kind of work through it with drawings, so that you don't mess up the pointers and where they point to, because that gets kind of tricky. So yeah, so if we're given a target, you know, in a basic binary search, we're going to just we're going to compare the midpoint to the target. And so if the midpoint is larger than the target, we know the target must be on the left side, so then we can discard everything on the right. So to discard, we just move our right pointer up until mid, or some people can do mid -1, but I'll stick to moving right to mid, because that's the way we're going to implement the binary search, and that's the way we have to implement the binary search later for these next 2 examples. So I'm going to do it this way. So I'm going to move right up to where mid is, and then we're going to recalculate mid. So mid is now in between, and so if mid equals target, then you return that index. So yep, 7 equals the target, mid equals the target. So yep, we can break out and return the index of -1. Alright, so let's see how we can do this for the pivoted rotated array. So yep, we have our left pointer, right pointer, and then the midpoint. And so what we're gonna do, instead of comparing it to some target that gets passed in, we're gonna compare the midpoint to the right side every time. You know, you could compare it to the left side every time, but just by convention, I think makes more sense to just compare it to the right side. Okay, so let's see, what kind of information does that give back to us when we compare these 2 values, the midpoint and the right point? So if the midpoint is greater than the right point, like we have in this case, 8 is greater than 3, that means there was a pivot at some point between 8 and 3. And we can, we don't even have to include 8. We can just say, everything like forward and on. So 9 to 3, there must be a pivot at some point in this part, if the right pointer is less than the mid pointer. So then we can discard everything on the left of the mid, including mid, so we can move left all the way to mid plus 1, and then we can recalculate the mid. Alright, and we do the same process, so mid is 2 and right is 3. So this is the other case now, the other way around, where mid is less than right. So in this case, then we can say that if mid is less than right, that means that this whole sequence was in ascending order. So you can imagine that the pivot must be on the left side. So you can move right to mid. And the reason you can't move right to mid minus 1 is, like as you can see in this example, if you moved right to mid minus 1, then you'd be missing out on looking at this 2. So that in this case you'd have to just move right up to where m is, to where the midpoint is. If you move it to m minus 1, then you could be overstepping and missing the pivot. So then we recalculate m, and our new midpoint is here, representing the value of 9. And so 9 is greater than the right point of 2. So then we're going to move left to m plus 1, like I said earlier. So here, and then we can recalculate m. Well, actually, we don't even need to recalculate m. Before that happens, we're gonna just iterate until left. So we're only gonna iterate while left is less than right, strictly less than. We're not gonna do less than or equal to. We're gonna do strictly less than. So then, in that case, once that happens, once left and right are the same index, then we can just return either we can return array of left, or we can return array of right. These are both pointing to the same thing, so it doesn't really matter if you choose left or right. And we'll see another couple examples, and you'll see that the left and right will always end up pointing to the same exact index when you break out. So it doesn't really matter if you do left or right, but just by convention, I think most people will choose to do left, because there's other variations of binary search where actually right will cross over to be less than left, and then left will be the correct index. So by convention, most people will just return the left array of the left pointer. Alright, so how does having duplicates, that's why there's a part 2 to this question, how does that change anything, or does it change anything at all? So now you can see that we have mid is equal to the right pointer of 8. So what should we do when they're equal, right? We never had that situation in the first part of this problem, because everything was unique, all the values were unique. But now what do you do if they're equal? So now you have to introduce a third case, and where mid, the array of mid is equal to the array of right. So what do? You should only decrement right by 1. So this will make your runtime a little bit slower on average, because in the worst case you might have to decrement right 1 by 1 by 1 all the way until the end. So obviously worst case could be O of n, but on the average case not much is changed in the time complexity of log n. So you see we're going to move right, we're going to decrement right by 1, and then we're going to recalculate mid. So actually mid ends up being at the same index, and now we see that mid is greater than 2. So we move left to mid plus 1, and then we move mid, we recalculate mid, and then we find that 9 and 2 situation again, and like the last problem, that means that we're going to have to move left to mid plus 1, and then then we break out of the loop again. We won't even be recalculating m. We'll just break out of the loop once left and right are the same, and you can return array of left or right, doesn't matter, they're gonna fall on the same index. And so let's just see another example where this might, just to kind of reiterate your learning. So we have mid at 7 and we have right at 8. So if we have, if mid is less than the right, that means that this whole sequence was in correct sorted order, so the pivot must be to the left. So we can move our right all the way down to mid. And then what we can do is recalculate M again, recalculate mid, the mid pointer. Now it's at 2. So then is 2, so 2 is less than 7, so that means the pivot must be happening somewhere between these two numbers. That's why we move right to wherever mid is, and then we recalculate mid to be 0, 0th index, and now mid represents the value of 8, and 8 is greater than 2, so in this case we move left to mid plus 1, and then left and right are lined up, so that's when you return array of left or right, doesn't matter. So hopefully that was a holistic algorithm walkthrough for you guys. I think you're probably gonna have to draw out these diagrams for yourself and kind of probably do exactly what I did here and step through to make sure your pointers are where you expect them to be, because when you're working with pointers, binary search is not really one of those algorithms where it's like something you can just like memorize, like every single line, every indent of it. You probably will need to draw an example real quick every time just to help you, unless you're like some super, unless you use a binary search every day or something, I don't know, unless you're like some competitive programmer. But yeah, for the most part, when you're working with several pointers, left, right, mid, then you should probably just draw it out and walk through it. So alright, hopefully that was a good explanation. Hopefully you guys know how to do both parts now. Yes, so actually I'm going to start linking the code in the description so you can see the way that I wrote it into code based on this English algorithm. So save you guys the trouble of having to find someone else's code, which might not even line up with the way that they thought through the problem. So alright, yeah, hopefully you guys can go and implement this now, and yeah, thanks for watching.